Everyone. So we are today on lecture 19 EE341 microelectronics. So what we are going to do today, we will continue the same topic of feedback. So which we started 2 lectures back. So I will give you a quick overview what we have covered in the last lecture, and will also build on top of it. So in last lecture, we have discussed about the sense and return mechanism or technique. We will build on top of it today, basically. Last time we just like a little bit we saw an abstract view, but today we are going to go a little bit more into detail. And also we saw the polarity of negative feedback, how we normally see the polarity of feedback, not negative feedback, the polarity rather of the feedback system in a circuits. So explicitly for the analog circuit. So we saw how we can see the polarity, whether it's a negative or a positive. We talked about those things. So what we are going to do today, we will focus on the same topology, which is sense and the return circuit, and we'll build on top of what are the sense and return circuits and how we are having. So we have multiple types. So let me start with the first one and then we can build from there. So first one, let me write a voltage feedback. What is meant by a voltage feedback is basically something like this, which we are seeing. We have a system. Let's call it same name which we're using. We have a system with a gain A0, open loop gain is A0. We are giving some input. Let's say I'm using just 2 lines just to clarify the point initially, and then we will go to the notion of 1 line. So we have an input which is basically giving an output, which is the voltage. Once we have a voltage output, so what we want to sense this voltage output. So we want to sense this, sense the output. Now we have talked in the last lecture when we want to sense the output and that output is voltage, how we can sense it? We can sense with the help of a voltmeter. And how we connect a voltmeter? In parallel. So we will take 2 signals. So we'll connect in parallel to measure the output from this potential. Why? Because we want to sense the voltage, and voltage all the time we plug a voltmeter in a parallel so that we can read the voltage without disturbing the inputs, without disturbing the circuit integrated. And then what we are doing, we are giving some feedback, which is K, which we all the time using. Okay, that's well and good. We give a feedback K, and what we are doing that it's a voltage feedback. We are feeding a voltage X, whichever the input here is a voltage. So we want to feed this back into our circuit, and this return circuit is also voltage. If this is a voltage at this node, this means X is also a voltage. If I call this thing as a U, just for naming convention, if X is volt, or let to be more explicit, if U is voltage, then X is also voltage. Why? You can see that I can add current in the current, voltage in the voltage. So once I am getting a voltage here, I can only add the voltage into a voltage system. So this is a voltage for me, since I'm just multiplying the output with the K, which is a unitless quantity. I'm getting a value U. And if U is a voltage, then this means if I'm going to add or subtract in X, this means the X is also going to be voltage. So what we normally do whenever we want to add a voltage or subtract a voltage, we also talked in the last lecture, the voltages can only be added or subtracted in the form of series, not a parallel. Parallel, we don't add voltages. So that's what, if this is V1, this is V2. So overall it will be V, and V will be equal to V1 minus V2. So we can have two potentials or plus minus, let me write whichever the configuration we want to use them. So now if we want to have a negative feedback the way we are doing, where our model was something like this, let me redraw the model for our clarity. This was our initial model, A naught going from here. I'm just now drawing a single line draw as opposed to the double line which I just draw for plus. It's going minus. So now you can also see the notions. Here, this signal I'm saying U, which is going as feedback. So I'm giving a negative feedback. So if I'm giving a negative feedback, and this is a voltage, so they are going to be in series. So how it can be in series? Like this, simple. And I apply my input somehow here, whatever the input voltage, let's say. So now this is the overall configuration of a voltage feedback. Now some points which need to be clarified. This voltage, which is coming in the first, that's related to the sense part. What I am sensing here. So what I am sensing here, I am sensing the voltage. That's why I put a voltmeter. So the first name in the voltage feedback, or this naming convention, this voltage means what I am sensing. So I'm sensing a voltage, and what I'm returning comes at this point. So at this moment, what I'm returning, I'm also returning a voltage. Okay, so that you need to be clarified, that this sense and return mechanism, when we talk about voltage feedback, this means I'm sensing the voltage, which is the first term, and I am returning the voltage, which is the second term. At this moment, it doesn't make any difference since both are voltage, but we are going to see a different variations or different versions where the things are going to be changed. But let's a little bit remain focused here. So in a voltage feedback, this is a overall a voltage amplifier. Right? If this is a voltage amplifier, what I need. What about the input impedance at this point? It's a voltage amplifier, and we know in ideal voltage amplifier, or input impedance should be equal to infinite. What about my output impedance? In a feed forward path, in a voltage amplifier, ideally, we want the R out should be equal to 0. So let me write. Again, I'm talking about ideal at this moment. That is going to be. But what about this K thing? K is a feedback path. In a feedback path, this is again sensing a voltage. Again, this K is a voltage amplifier. So what should be infinite? Input impedance this point, it should be again infinite. And what should be input impedance on this side? This should be 0, since it's again a voltage amplifier. Okay, so this we need to make sure that feedback path and feed forward path have to be taken individually. A naught is a feed forward amplifier, a voltage amplifier, and input impedance should be ideally infinite, output impedance should be 0 ideally. And the output, the feedback path, is the input impedance should be infinite since it has to amplify the voltage, and the output impedance will be 0. And in totality, this voltage feedback, when we put in the negative feedback configuration, it becomes a voltage sense amplifier. So now our main goal is that we know how the A naught open loop calculation comes, how the feedback individually can operate. But our goal is that when we connect this in a feedback sort of stuff, how the input and output impedance changes, how the gain changes. If you recall from last lecture or lecture before that, we have seen the common gate amplifier and we tried to see the input impedance and output impedance. And that time we saw, okay, input impedance and output impedance for the common gate amplifier was changing when we connect in a negative feedback or in a feedback configuration. So we also now want to generalize that how the input impedance, output impedance, and gain changes when we connect in a negative feedback. So that's what we want to analyze in this configuration. Okay, so we will analyze effect of feedback, basically effect of, explicitly here we want to talk about negative feedback, so I can write negative feedback on gain, input and output impedance. Okay, so we will do this for multiple combinations, but before we do this, I want to describe all those 4 different versions, that voltage feedback, voltage current feedback, current voltage feedback, and current feedback. But again, this voltage feedback is equivalent to what we have seen in the last lecture, is a voltage amplifier. Okay, and what we know about voltage amplifier in general, ideally again, the input impedance should be infinity, output impedance should be 0. So if we try to achieve these 2 things in a system where the input impedance starts becoming infinite or a bigger value and output impedance start becoming smaller value, this means we are moving towards a voltage amplification, or it will assist in amplifying the voltage. Now let me just a little bit go through all those configurations. The first configuration we have seen, and then I will come back to the gain, input and output calculation for this small network. So let me just, yeah. So here we are now, we have seen the voltage configuration. Let's talk about the second configuration, which we can mention as about current. Let me just follow the same with the book is following. Is it current or voltage, or it is voltage current? So it's first talking about voltage current. So the second one is basically voltage current feedback. Okay, so a voltage current feedback, what is this first voltage? This is for the sense part. This is for the return part, right? So let me redraw the circuit and then we can see how the things are happening for us. So I have again something, let me draw it here. I have again some circuit where we have some input is coming. I will tell the input what type of input it is, but what we know, sense part is going to be some body here. Okay, this is some body, right? And it has some gain. It's a voltage current. So what is meant by voltage current? This means this output in this case is going to be voltage. Make sure this thing, the output is voltage, because I want to sense the output at this point. So sense thing is output, and how I'm going to sense is I want to sense our voltage. I'm going to sense parallel. Same which you just do in the last one. It's the same thing. So we have output path is the same. We have something parallel and we are putting here a K here. Okay. Now, what about the input side? Input side is what? Current. It's not a voltage. So the input side is current, and when I'm talking about input side is a current, how I should join? Whenever you know that you want to add or subtract two currents, you add them or connect them in parallel configuration. Okay. So this means these 2 points, this one, which is X again, and the U point should be connected in parallel. And also we know if U is current, X is also current for us. And that brings us to another notion. Let me first connect these two. So if I want to connect in the parallel, how I will connect them? I can just directly do this thing. This is my X, which is coming as an input, and I can connect them in parallel. So this will be connected to, I was using the red again to connect these two parallel, and so the dot is basically joining where I am making a signal. Okay? And that's where the connections are meeting. And okay, so now where is the what I am giving an input? I just mentioned if this is a current, X is also current, so I am applying a current. So if the current is being applied parallel to both points, since they are connected in parallel, I can say I in. And since it's a input is current, this is input, which is a current, and output is a voltage. What type of amplifier it is? From those which we have seen in the last lecture, it's a trans impedance amplifier. Input is in current, output is voltage. This means the gain is going to be something resistive. So I can write R naught instead of A naught. So that you have to be clear in this configuration that in voltage current feedback, the notion is that output is voltage because I'm sensing a voltage and I'm feeding a current basically, so that I can get the information which is required. So this is ultimately a trans impedance amplifier. Okay. In a trans impedance amplifier, just for a notion sort of stuff, ideally we want on a feed forward path, the input impedance should be equal to the Rin. Again, I'm talking in ideal world, the input impedance should be equal to 0 in a trans impedance. The output impedance should be equal to infinite. And for the feedback gain, for a feedback path, is basically at this moment we need to be clarified what it is doing. So again, it's so it's 0. Yeah, let me just 0 here. So you need to also take into care how you are going to feed that path from this side here, and you need to identify these things. So here, this ideal world, this input, this the input impedance from this side should be infinite. Output impedance from this side, since it's going to feed into the current, it's also going to be infinite. So that's what we need to make sure, because the Y is voltage, the voltage is being fed here, it's going to be multiplied by the sum factor, but on the output side, it's a current. So output current, this means again the output impedance should be infinite. So this for the feedback path, this is infinite, this is infinite. But again, we are at this moment we are seeing individually what should be the input and output impedance for the feedback and the feed forward path. We will later in today's lecture discuss about how the input output impedance changes when we connect them in the feedback path. At this moment we are seeing individually. Okay, but the notion which should be clear, that is a voltage current feedback, which is also a trans impedance amplifier for us, and we can use this in the configuration. Also, one important thing, since we are taking an output in parallel, so or sensing an output in parallel, we also call it shunt and we are returning or taking the input side also in parallel, or return paths also in parallel. So we also call shunt amplifier or shunt feedback. So this is also commonly called as voltage current or shunt feedback. If we want to go back in the first one, when we have voltage feedback, we can also write it as shunt, because we are taking the sensing an output as a parallel shunt, and we are feeding back as an input the series. So we also call shunt series feedback. So these are all the name convention we use. So the third one for us is basically current voltage. Now, all of you might be already having an idea what should be in current voltage feedback. So sense is basically again current. So the output is current. This means this is a sense part, or this is a series part, because whenever we want to sense the current, how we sense the current? We sense the current in a series, or using an ammeter all the time. It's connected in series. So let me again draw something. Let me use the same mark. So I have here, again, I'm not drawing, but it's inside, since again, there should be something different, not a not, because we have voltage to current, current to voltage, or voltage to current, we just can see now. Now, output is what? We are sensing a current. So output should be I out should be, it should be I out, some sort of stuff. So output is in series connected to something. Okay, and what should be that thing? If it is in series, we can connect like this one, which you just did now in small time. So here we can have a series connection. Okay, so we have a series connection, and in the series connection, this input is output is current here, and what should be the input? Voltage. We are feeding, or we are returning basically a voltage here. So that's what we can see, series, and whenever we want to add or subtract voltage, what we do? We connect again in series. So it's a series feedback, and in the series feedback, how I should connect? I should do something similar. Yep, like this one, and here and here. And so what we can say, input is voltage, output is current. What type of the name it is? GM, transconductance. So it's a transconductance amplifier. Okay, so it's a transconductance amplifier, and ideally, if we just see individually, this is a GM, a transconductance. For the transconductance, the input impedance should be what? The input impedance should be infinite, because it's taking a voltage, and output impedance should also be, what should be the output impedance? Since we are taking the current, the output should also be infinite, again, ideally. And what it is taking, the K is ultimately taking the current here, because we are feeding the current here. So for the current, this input impedance should be equal to 0, and the output impedance should also be equal to 0, since we want this voltage to be amplified. But again, make sure we are at this moment seeing this as a feed forward, and this one as a feedback. We didn't still talk about the overall impact of feedback. We just see the individually what type of amplification is happening. So it's a series, and we have a sense and return, and not, this is commonly a transconductance amplifier, which we have seen. And let me talk about the fourth one also here, since we have some space. We all know familiar what will be the fourth one. Fourth one, definitely the left one is current configuration. current feedback. So in current feedback, what's going to happen? We have a sense one. The first one knows for sense. So sense current, return current. Okay, sorry, return current. Or we can say if we are sensing current, sense current means in series and returning current in parallel. So it's a series parallel or kind of series shunt. Series shunt. So it's a series shunt configuration for us, or series shunt feedback. If I want to, sorry, if I just want to draw the configuration, how it's going to be. So we all have some idea that again, we have some sort of configuration, which is going to be in a form of a current sensing. So let's draw the circuit. Again, we have this time since a current to current, I can write instead of AI something, some gain. And how I am taking an output in a series. So this is my I out again, which is what just here. Okay, so I can take this one, have some K factor, connect here, and this one connect here. Okay, and the output, this is a current, and I am getting also current here. And how they are adding in parallel. Okay, so if they are in parallel, let me use the other one. So parallel means this one will be connected to this point, and this point will be connected to this point. And I'm applying some current on this 2 points, so it will be equivalent. Yeah, this is a current, for example, I in. So this is I in, this is I out. So we have a series shunt feedback. We have a current input, we have a current output. So if we want to talk in terms of input output individually, we are going to have some impedance. What will be this impedance? This impedance should be ideally equal to 0. Output impedance ideally should be equal to infinite. For a feed forward path, for a feedback path, again, it will be something equal to 0 and something equal to infinite. Okay, it's a current one. So that's what you should be clear with all these 4 configurations and the input and output impedance. Make sure to clarify these points before moving forward. We also discussed this input and output impedance relation in the last lecture. Okay, but that time we just skimmed through, but today we are talking in more detail about these things. So let's move forward towards the now see the response, how the input impedance, output impedance, and gain in generic changes in all these 4 configurations. So we'll start with the voltage feedback and try to derive the relations, and that will be helpful by applying into some of the examples, which we will just bring in a moment also. So let's start. That's the third one. So again, I'm going back to voltage. I'm just starting voltage feedback. So as we mentioned in a voltage feedback, we have, I will draw again the configuration. So this time I will draw relatively, let me draw the same configuration again so that we don't have any issue. So it's a voltage A0. We have sensing is in parallel. Let me write this voltage as Y. And we have something which is in parallel. So parallel to what? Parallel to K, which is a gain. So I'm feeding voltage here. So this voltage will go here, and I am returning in a series fashion since it's going to be adding voltage. So we can do it this way. Okay, so here we have, and we can call it as an X. This path which is returning is U. Okay, just for simplification, we meant this thing, and if I want to have a little bit idea that now what I want to find the gain of this new configuration input impedance and output impedance. Okay. But before that, we need to know what is the overall, let's say, the gain of the system with the before the feedback. What was input impedance before the feedback? What is the output impedance before the feedback? That we need to know. So that's why, first of all, we need to identify it's a voltage feedback. This means it's a voltage amplifier, which we all just know. Okay, amplifier. So in a voltage amplifier, the gain, open loop gain was what? Without feedback, let me write, without feedback. When there was no feedback, in ideal world or in this configuration without feedback, the gain was what? Equal to A naught, right? What was input impedance? If you remember, we also talk about a realistic model. In generic, in ideal world, input impedance should be infinite in a voltage amplifier and output impedance should be 0. But we are not living in ideal world. So we talked about there should be some impedance which is in parallel here. I just try to draw it. It's more like an inductor. So I just need to create some space here. Yeah. So, okay, so in reality, this A0 amplifier have some, for example, impedance Rin. For example, I just give a name Rin, which is actual impedance. So there is going to be Rin can be a very much bigger value, but it has, or let me, instead of Rin, let's write R. So we just don't confuse. So it has something R, not R, Ri. So that's this impedance is Ri. So it previously it had an input impedance which is equal to Ri. Okay. And output impedance also we have some output impedance instead of 0 we have something in series here. So if I want there's something RO connected. Okay. So R out is equal to RO, some resistance we also have. In ideal world, this will be equal to infinite. This R out will be equal to 0. But we are in a realistic world, so we are saying that A naught, the feed forward, has some input impedance Ri, which is a higher value, but it's equal to Ri, and output impedance R out for a feed forward path is Ro. Whereas still, we are saying that this impedance, which is seen at the feedback path, is infinite. We are not concerned at this moment, and this impedance is 0. But we are concerned about what is the input impedance at from this point, from this overall, when we connect this A naught and K for this circuit between these two plus and minus, what is my input impedance and what is my output impedance? So let's talk about these things. I feel before moving feed for input impedance, output impedance, let's find the gain because that's pretty much more easy. But now what I will do, I will shift to a simplified diagram. Instead of having this configuration, I will try to do that same diagram which we were just analyzing. Might be more easy for us to analyze. So that is more for the understanding part, how the series shunt are working. But now we can also have our whole diagram. That okay, we know that this is A naught. Now also you can see whenever it's A naught written, you can understand what does this mean basically. This is the voltage in input, and here we have some current. This is also X. So what we normally write in this configuration, which we have previously seen multiple times, that our Y over X or V out over V in is equal to what? Will be equal to A naught divided by 1 plus K times A naught. And this is the gain. So you can again derive it. So in a feedback gain, in a feedback system, the gain is reduced by the factor of 1 plus K A naught. And we also already talked about K times A naught is a loop gain. So our feedback path, in a feedback system overall, the gain gets reduced. We know this thing. So that's first thing. So now come to the input impedance. Input impedance. So let's redraw the circuit by plugging this R in. For our simplification, we can have this circuit be in. So we have something current which is being flowing here. Same thing. Now here we have some resistance which is being part of the amplifier R. We said Ri. Okay. And we have here K going as a negative feedback. Right. So we want to observe basically now the input impedance of the system. So what will be the input impedance here? We're not talking about the A naught because A naught has Ri, but we want to talk about this overall system, which is this one. So if we see there's some current flowing here. So R in should be equal to V in by I in. Okay. Same thing we can see. R in is equal to V in by, from this circuit also. R in is equal to V in by I in, and we can give some names here. So here we can call it as VF going here, or U in this block configuration, the circuit configuration, we can have VF. So what we can say this thing that this potential V in is equal to, I will just mention also in the circuit, but let's first, this V in is equal to some potential which is going to this point, to the amplifier and the feedback one. So the overall V in is equal to, if I just want, might be more clear from the above this circuit that how it's happening. So this is some potential which is V in. So these two terminals are V in. So where X is equal to V in. So this V in is equal to two potentials. What are those two potentials? The potential which is going to the amplifier, this point, and the potential which is on the K, the gain path, or I can redraw the circuit like this one. So we have two potentials. Let's write the first potential as VA, and the second potential as the U or VU or VF, let's say. And this overall, we are calling it as VE. So you can see this thing equivalent to this figure. So here the potential which is at this point is VF, okay, and the potential at this point is VA. So V in is equal to VA plus VF. Same thing here, this V in and this potential which is seen at this point, because they are feeding back, is going to be VA. So we can write V in is equal to VA plus VF. So we need to mention what is V in and what is VA. That is important for us. So what is VA? VA is the current. This is I in and this is going to Ri. So this all current multiplied by this resistance, because the resistance is going to be very much huge. So the VA we can write will be equal to I in times Ri. Okay. And what is VF? VF is being, this is the same potential multiplied by A naught multiplied by K becomes VF. So we can write VF is equal to I in Ri times A naught times K. Okay, is it clear? So make sure this point. So now we can just plug in the values. The V in is equal to I in Ri plus I in Ri A naught K. Let's take the things common. I'm using a different color to identify the thing. So V in equal to I in. If we take the common I in and Ri also common, we will left with 1 plus A naught K, which will lead to V in by I in, which is the equal to R input impedance of the closed loop system, Ri times 1 plus A naught K. So our input impedance, by utilizing a closed loop feedback and negative feedback, enhances in a voltage feedback configuration. And that's very much important, that input impedance increases by the same factor, which is loop gain, 1 plus loop gain, the same thing by which the gain was reduced. Somehow, if you remember, similar expression we got in the common gate configuration, where we have ultimately a trans impedance amplification, and we got that trans impedance amplification, and we got that, okay, the input impedance there was somehow uh, decreasing and the output impedance was increasing. But here what we are achieving in the voltage configuration, or in the voltage amplifier, when we connect enough feedback, our input impedance increases. And is it good thing or a bad thing? We just mentioned some voltage amplification, and for the voltage amplification, in reality, we want the input impedance to be as high as possible. So this means ultimately, this is a good thing. It's supporting or the notion that the feedback ultimately make the circuit desensitized to the environmental variable. So that's a positive thing, a good thing for us. That's why the feedback helps in achieving the cause. What about the second thing, output impedance? Let's do the same thing. Now we are having the same circuit. We are assuming we don't have any input impedance, nor rather we just have an output impedance R out. So, okay, in the model, we just have an output impedance. Okay, let's not use the black color, use a red one here. Okay, so now what we are having, so we want to find the impedance. We can short the input, so we can ground it. So here, negative feedback, same thing, K is coming. And what we can put in, we can plug a test source, which we all the time do. For the input side, we did ultimately the same thing, but there was no as such explicitly required. So we can find Vx here, and we can find Ix. So R out will be equal to Vx by Ix. So can we find the Vx by Ix? So the current Ix will be equal to this node minus this node. So it's going to be Vx minus, let me say this point as let me give any name, VAR. So not to confuse with any other name, VAR divided by R naught. Make sure this is clear. So what is VAR? And then we can plug back. This is one. So VAR is the voltage which is at this point. So this is Vx times K naught minus, so 0 minus Vx K naught. This is this point. So which is equal to minus Vx K A naught. Plugging into this above expression, Ix will, again I'm using a different color, Vx minus will plus Vx times K A naught divided by R naught, which will lead to, let's take the Vx common, 1 plus K A naught equal to Ix by R naught, right? Which will lead to Vx by Ix equal to R naught divided by 1 plus K A naught. So what's happening here? Without feedback, the output impedance was R naught of a voltage amplifier. Well and good. But after adding the feedback, the voltage output impedance reduces by amount 1 plus K A naught, the same thing of our loop gain. And that's again a good thing. because in a voltage amplification, we want in general the overall output impedance to be equivalent to 0 or a very much smaller value, and the negative feedback helps in achieving that thing. So it's a positive thing again. So we concluded that in a negative feedback, in a voltage amplifier or voltage to voltage feedback, the gain reduces, okay, by 1 plus K naught times. Rn increases by 1 plus Ka naught times, and the output impedance also reduces by 1 plus Ka naught. So this is a generic, but for a voltage feedback. So we can say this thing, this is generic for voltage feedback. Okay. So now we can do, I guess, let me just see, either we can do one example. Rather, I would like all of you to do this couple of examples. They're very much nice examples. Let me write the number. So example 12.15, that basically talking about the active load and finding the gain and doing the input and output impedance for those differential active load configuration. And similarly, I guess followed by 12.16. They are pretty much straightforward examples, but nice to do. I would highly recommend all of you to go through to revise your again, they're doing an input impedance, output impedance for a differential with active load, and then doing the same thing for the feedback configuration by just applying the same, which we just figure it out. So make sure to do this thing. And what we can do now, we can move toward the second configuration. I feel so. The second configuration for us was voltage current configuration. I will go a bit quick in this voltage current configuration because something I will leave for you that you have to analyze yourself, the behavior. So in a voltage current feedback configurations, let me redraw the circuit quickly. That what's happening. So again, we were having something like this. Now we know it was R0 since a trans impedance amplifier. We were sensing the voltage, so voltage was output, and we are connecting it in the parallel configuration. So here we have something in parallel. We have something K, and it's a current feeding current, again parallel. So we have something I in here. I in going to this point, the same I in will be feeding to this thing. So I'm making these dots to make sure this point. Right, so here we have some current and this current which is going this point, let's write it IF. And here this current is I in, and the current which is going to go here will be I error, for example. We want, again, this infinite for the gain one, and output impedance also is infinite since a voltage input current output. So it's a trans impedance overall configuration. So let's talk about the gain first. So quickly, V out is what? V out is equal to, in the closed loop configuration, it's I error, whatever is coming, times the R naught. Simple for us. And what is IE? IE is equal to I in minus IF. Since they are both subtracting together, it's a negative feedback, so we can write I in into R naught. And what is IF? We can just see IF can be represented in the form of V naught and K. So K is ultimately equal to IF is equal to K times V naught. So K times V naught into R naught. And the gain of a transimpedance amplifier is what? We have V out by I in. So we are interested in finding V out by I in. So we can take V out plus K times V out R naught divide equal to I in R naught. So if we take V out common here, it will be 1 plus K R naught divide equal to I in R naught, which will be equal to V out by I in equal to R naught divided by 1 plus K R naught. So it's a gain of a voltage current feedback. So it's a gain of a voltage current feedback, which was in open loop configuration equal to R naught, but in a closed loop, it again reduces by the amount 1 plus K R naught. So the same expression. So all the time gain gets reduced by the open loop, by the loop gain. 1 plus K naught times, 1 plus K R naught times, or 1 plus K GM times, whatever the gain it is. So gain all the time reduces by the loop gain, amount. So that's what we need to identify, whether it's a voltage, whether it's a voltage current, whether it's a current voltage, or whether it's a current configuration. So all the time our gain is going to be reduced. So that's what we know about the gain. So what about the input impedance now? We can see the output impedance will follow the same behavior. Since it's a resistance, we will assume an R naught here, and the R naught ultimately will get reduced. So in a transimpedance, in a voltage current feedback configuration, the R out will be reduced by the factor 1 plus K R naught. But what about the R in? So we need to see the R in. So let's draw for the R in. We can have this R naught here. Since it's a transimpedance amplifier, we want the input impedance to be very much smaller, 0. So we can have mimic this thing with the help of a R in series, a very small resistance for a realistic configuration, which we have seen in the previous lecture. And K gain going here. So we have some configuration. The same I'm just drawing for an input impedance calculation. And we can have some current, let's say now IX. Okay. Whatever you want to give name, but it's going to be IX, and we want to find VX. So our R in, and this is equal to this side output. So our R in is equal to VX by IX. ठीक है, हमारी जो R in होगी वो होगी VX by IX. So now again we know that the voltage which is at this point is equal to IX times R in. V out will be equal to or rather the current flowing from this point will be Ix times R naught. So V out will be Ix times R naught, and the IF, which is at this point, will be equal to K times that Vx, since the Vx is coming from here, Vx by Rn times R naught. So just to make sure all of you are on the same page, we have a potential Vx here. So the current which is flowing through this point will be Vx by Rn. So this Vx by Rn get multiplied by R out to become V out. So this has become Vx by Rn times R naught. This becomes on the feedback path, and this becomes this is multiplied by K naught. So IF is equal to K times Vx by Rn into R naught. So we have this expression, we can directly map into Ix, which is equal to Ix equal to, we just saw the Ix is equal to, So we just mentioned that the current which is flowing through is equal to Ix minus If is equal to the current which is flowing through this one, which is Vx by Rn. Okay, so Ix minus If. So you can see this current is feeding here, this current is splitting into two, or we can write Ix is equal to If plus Vx by Rn. ठीक है, So that's why we write Ix minus If is equal to Vx by Rn. We just figured it out what is If. So it was equal to Ix is equal to K times Vx by Rn R out plus Vx by Rn. Taking the Vx common, we will be left with Vx and Rn also common. We will be left with 1 plus Kr naught. Okay, and what we are interested to find? We're interested to find Vx by In. So from here, Vx by Ix, sorry, not In, Vx by Ix will be equal to Rn divided by 1 plus Kr naught or Kr in. In a voltage current feedback, the original input impedance of an open loop gets reduced by the factor 1 plus Krn. Again, I am just missing up, not Rn, R out. Sorry, so this is correct. So 1 plus Kr out. So our input impedance get reduced by the factor 1 plus open loop gain, or 1 plus, sorry, loop gain, not open loop gain, 1 plus loop gain. So our input impedance get reduced in this configuration, and this is the same thing which we have seen for the common gate. So this is the common gate configuration trans impedance amplifier, where the input impedance get reduced and output impedance get enhanced. Sorry, and output impedance also get reduced. So that's what we are tapping here. Is it good? Yes, we need to see that in a trans impedance amplifier, we want the input impedance to be as low as possible, equal to 0, and the negative feedback, voltage current feedback, is ultimately supporting that thing. So input impedance, which is Rin, is doing this thing for us. So this is new, closed loop. And if we do for the R out by following the same similar which we just did in the last one, the R out also got reduced by the same factor. Okay, so that's something which we just need to ensure that our input impedance reduced in a voltage current feedback. Okay, so what I will do, I will just leave the current voltage and a current on you. You can just go through the book, and if you need, you can derive, but they are pretty much straightforward. What I will do, I will write all of those configurations for your information. So I will draw one complete table for all of those configurations. So might be that's more better. Sense, return, let's say common configuration, we can say a type of amplifier. Gain and input impedance, output impedance. Assumingly the original input impedance was R I, and this is R O. So what I am meaning that in open loop the input impedance was Ri, and open loop the output impedance was R out. Okay, so let's fill this table. If we have voltage, which we just seen, voltage. The type of amplifier is a voltage amplifier. Gain gets reduced. So if we have previous gain of A naught, the new gain will be 1 plus K A naught. And the input impedance, what we saw, the input impedance get enhanced. So if it original was Ri, new will be 1 plus K times A naught. And what about output impedance? Get reduced. Original was R naught, new one will be. Okay, and it's also called what we normally call it as sensing is shunt and return is series. So shunt series configuration. So इसको one कह देते हैं. What about the second one? Second one which we just saw today also was voltage, current. So we are sensing again a shunt. Let me use the same color. We are sensing a shunt and we are feeding also a shunt. Common name of this configuration is we are input is current, output is voltage, a trans impedance. Gain gets reduced. Gain all the time gets reduced. If we have original R naught because the trans impedance, gain will be reduced by this amount. What about input impedance? Input impedance gets what? Reduced. So input impedance, if it's Ri original, it's get reduced by the same time. What about output impedance? Output impedance also get reduced because the same configuration. Okay? So we need to remember these all things, or we can derive it. It's pretty much straightforward, but just unless you again do the thing, you understand why and what, should be pretty much straightforward. Current, voltage. Just the concept is the same. When you want to sense a voltage, you can sense the voltage in a parallel configuration using a voltmeter. When you want to feedback the voltage for return path, it can be in series. So it's a parallel series, and the input and output impedance follow the same pattern. Vice versa, when you want to sense a current, you sense a current in series with a very much small resistance. When you want to feedback, you want to feedback or return in a parallel configuration because the current add in parallel. So that's what, and then that time's output impedance should be infinite. So these are the simple things which we just need to understand. So the current in series we sense, and voltage we series. So it's a series configuration. What type of amplifier? Trans conductance. So here we have to just, what will be the input impedance? Again, sorry, gain will be GM 1 plus KGM. So you can, if you have any difficulty, make sure to update me. We can do in office hours window. And what about input impedance? Now input impedance is going to be what? Ultimately, or input impedance going to be enhanced by the time of gain, which is KGM, loop gain. ठीक है? And output impedance के साथ क्या होगा? So output impedance will be, that's first time we are seeing the output impedance will also be enhanced by the same factor. Let's make sure to get clarified this point. The output impedance one might be, we didn't see this one, so just make sure to see this thing. See this, how it's going to happen. Then comes the current path. In a current, what we normally call it as, we are sensing current, so we are doing series, we are feeding in shunt. Okay? So series shunt, what is this known as? Current amplifier. What about the gain? Gain, whatever AI will be again reduced. Gain all the time has to be reduced. At least one thing we know, the gain reduced, that's a negative thing, for example, if I want to say. But input output impedance, good thing, positive thing, better control, which we talked in the feedback. What about the input impedance? Again, think over it before we want. Input impedance is current. In reality, what's happening in the input impedance for us? Think over it. We want zero, so ultimately it's also supporting our claim. So the input impedance get reduced by the same factor. And what about the output impedance? Output impedance get enhanced by the same factor. Okay? So output impedance get enhanced by. See, again, as I said, make sure to see these two behaviors. The rest we have derived already, but make sure to see these things. So just make sure to go through this lecture. Again, the lectures are built on top of each other, so you have to clarify these simple things, and going a little bit slow on pace. Next lecture, what we are going to do, we are going to cover the stability things of a negative feedback and the review of a Bode plot. Again, a little bit have seen a different perspective, and we'll do a couple of examples, but make sure to cover this content so that we can have a better understanding for the next topics. And also we will update about the next quiz. It will be preferably on coming Monday for section 1 and Wednesday on section 2, but we will update on LMS. Thank you. And again, if you have any concern, you can send an email, you can come in an office hours. We'll be more than happy to solve your query. Thank you.